So hi everyone, welcome back. Today we have Louis from Zama. Louis, would you like to introduce yourself?
Yeah, sure. I'm a blockchain engineer and a researcher as well at Zama. Quick background about myself. I graduated from the University of Montreal. I did my undergrad studies there, during which I had the chance to have a professor who was interested in blockchain. And so I got to follow a course from him, and with that kind of niche expertise, I made my way into Zama, where I've been contributing on the blockchain side. So work on the FHE VM, and now I'm taking more of a research-oriented role, doing research on verifiable FHE.
Cool. I guess the topic today is ZK FHE. Maybe just to start from a high level, why is ZK FHE relevant and important both in Web 2 and Web 3?
Yeah, that's a good question. I think so. Just about the nomenclature, I'm going to be talking about the verifiable FHE because in verifiable FHE we basically slap a snark onto FHE, and there's nothing really ZK about it. So as cool as it sounds, I prefer that name, verifiable FHE. So I think in Web 2 there's a necessity for verifiable FHE, and that comes from the fact that in real life deployments there are attacks that can be mounted against like client-server paradigms that use FHE. And these attacks are thwarted by verifiable FHE, basically. I also think there's a maybe interesting use case that doesn't need maybe FHE right now, but it could be fun to explore, which is the one of ZKML, which has gained a bit of traction recently. And I think that, ZKML, what it allows you to do is to let someone prove that a known model has been used correctly to do, for example, inference, while hiding the user's inputs. And I think there's an interesting, so I'm no ML expert here, right? So I don't know if that really makes sense, but I think if you want to slap FHE on there, maybe like encrypt the model weights or something, you can get something pretty interesting out of that.
It's basically solving the same problem, right? You want to hide data. ZK does it off-chain. That's how they're hiding, but still proving some kind of like machine learning, right?
Yeah, but as far as I get it, like in ZKML, the model weights aren't hidden. Right, you give the model weights to the user, they hide their private input, maybe their healthcare data, and then they give you a proof that it was correctly executed together with the result. But maybe like the weights are proprietary.
Yeah.
Right? Maybe like the model provider wants to hide the weights. So I don't know. Maybe that
makes sense. And I think in FHE ML, at least you can hide both the data and the weights, right?
Yeah.
I think this is definitely more interesting, or I guess like a different property. From ZKML. Yeah.
So yeah, I think there could be something nice to do there.
Oh, I was going to say, So, why do you need FHE to be verifiable?
So in that case, I guess you just want to give a proof to someone that you correctly made the inference.
Right. Because if you do the work, I don't know if you are lying or not, right? You need to somehow prove that you did the work correctly.
Yeah, exactly. And I think in that case, you could also use ZK to hide the user's inputs.
Mm-hmm.
Only have the encrypted weights and have a plain text user input, use ZK to hide it and still prove that you correctly did the inference. So I think that's that could be a nice use case for Web 2. And in the context of Web 3, I think, it's not as much about security and necessity, and it's more about like some fun use cases, like roll-ups, The way I see it, I don't think we're going to see FHE running on L1 validators in like super decentralized networks such as Ethereum, It's sort of like goes against the ethos that Ethereum has of being super decentralized and anybody can stake. You can do like staking at home. You can run like these validators on Raspberry Pis or whatever.
Right.
And since you need quite heavy machinery to perform FHE ops, I don't think we're going to see FHE on L1s. But with verifiable FHE, what you could do is you could have a semi-centralized network, a layer 2 rollup, with a couple of like rollup operators that have heavy machinery, maybe ASICs or whatever. And they could do the FHE computation on the layer 2, post like the transaction data and resulting state roots on layer 1 or some DA layer or whatever.
Yeah.
And whenever there is a dispute, they could do this like optimistically. And whenever there's a dispute, they could do like these ZK fault proofs, which is basically a mix. So this whole rollup architecture is a mix between optimistic rollups and validity rollups. And I think this is a good use case for verifiable FHE in the context of Web3.
And just to clarify, this is not a ZK FHE rollup, right? The same as a ZK EVM rollup. You're talking about a optimistic rollup with ZK being used to do some kind of fraud proof, right?
Yeah, exactly.
Okay, so this is the hybrid part. Okay.
Yeah.
And then you just prove the fraud like a
Yeah,
state transition over ZK.
So if you've got this like a staked rollup operator and a staked whistleblower or watcher, and then the whistleblower says, okay, I don't agree that this computation gives this result, then the staked operator has like, I don't know, 1 week or a couple of days to give a proof that this transaction indeed gives this state root. And if the proof verifies on L1, then the whistleblower is slashed. If it doesn't, then the rollup operator is slashed and somebody else can pick up the work.
That makes sense.
Yeah.
No, I guess like we can dive deeper into this topic of ZK proving FHE, right? I guess maybe just right before that, you mentioned the other reason why we're doing verifiable FHE is to prevent certain attacks, right? Could you maybe mention what type of attacks we can do today?
Yeah, sure. So in the context of Web 2, FHE is only secure in what we call the semi-honest or honest but curious model. And that means that the server, so if you have this client and server paradigm in FHE, where like the client wants to do some computation of outsourcing, but they want to maintain privacy, they basically encrypt their data and ask the server to perform the computation. And in this context, it's only secure when the server doesn't do any funny business, So maybe I can give an example. So say you're a client and I'm a service provider and I say I provide like an encrypted calculator or something. And you ask me to do an addition and you give me 2 ciphertexts, one that encrypts 0, one that encrypts 2. And if I were to be honest, I just perform the addition homomorphically. I learn nothing about like the input or the result, send you back the result, you decrypt it, and you get 2, and everything's fine. But if I'm malicious, I can replace one of your ciphertexts, by another ciphertext of which I know the plain text. So say I replace the first one that was encrypting 0 by another one that I know was encrypting 0. I still do the addition, and I get the result, which is an encryption of 2. I can still send you back that result, and you decrypt it. And since you got what you expected, you don't have any weird behavior, You just like move on, you do your stuff. And so this way I kind of learned that your first ciphertext was 0, which I wasn't supposed to know in the first place. And conversely, I could like replace your ciphertext of 0 with one that encrypts 1. And when I return you the result, it's an encryption of 3. And so you didn't expect that, and you're just gonna like maybe come back to me and ask me to run the same computation again. And then I learned that what you encrypted in the first place wasn't 1. So these reaction-based attacks are really like putting real-world FHE deployments in danger. And notice how like they don't exploit like the cryptographic primitives upon which FHE builds.
Yeah,
they really attack the whole system, like the reaction.
Yep, and this is also really because you as a centralized party, you could do these injection swapping, right?
Yeah, exactly.
So maybe like talk about why ZK helps.
Yeah, sure. Yeah. So with verifiable FHE, what you could do is, as a server, not only I would perform the addition that you asked me to do, but also I would generate a proof, that I performed this addition correctly on the inputs that you gave me, and I did nothing else in that addition, right? So I didn't like modify the ciphertext that you gave me as input. I didn't like add another addition, or I didn't like mess with the result afterwards. And so what you could do with that proof is verify it in the first place. And if it verifies, then you can decrypt, then you can do whatever you want. You know that what I did was correct. And if it doesn't verify, then you just stop talking to me,
Yeah, that's pretty clear. So it's some kind of guarantee.
Yeah, exactly. Yeah. A guarantee over integrity of the computation that was made by the server.
Yeah. Great. I guess now to, what's the current state of verifiable FHE? What kind of work has been done by other people? Just if you can sort of paint the picture.
I think there's a nice paper out of ETH Zurich that was published, or not published, but put out online in 2023, I think. And they do, so basically they explore a wide array of options to obtain computation integrity of FHE. They go even into like using trusted execution environments to get the integrity. And they also try to do VFHE using snarks, but they limit themselves to the BGV scheme, which is an FHE scheme that has quite efficient level mode, but a very costly bootstrapping. So they get some nice results. They can prove that FHE using BGV was executed correctly quite fast, and like their verification using, say, Grod16 is quite fast as well. It's very efficient, but the result is only good for bounded depth computation, right? You can't use BGV to compute indefinitely, or you can, but it's very costly.
Yeah, I guess to explain the audience, the idea is, for example, for smart contracts, right? You don't know ahead of time how many operations you'll be doing.
Yeah, of course. Yeah, so the
So
idea
you need
is
infinite depth. Yeah.
Yeah, you do need infinite depth. You need an efficient bootstrapping because it's not like we can't tolerate like having smart contracts only being executable like a few times before they're good for trash, right? Like you need for them to live as long as the blockchain lives, and that may be, I don't know, infinite.
Yeah. So now that you mentioned bootstrapping, could you maybe just explain what a bootstrapping is from a high level, why it's needed, and maybe talk about your research specifically around verifiable bootstrapping? Yeah.
Sure. So maybe it's best to take a step back and go back to the encryption in FHE. So when you encrypt a message in FHE, you add some noise to it, right? And that's what makes it secure. And whenever you compute on ciphertext, this noise grows, right? So if you get two ciphertexts as inputs, you add them together, you do some multiplication, the noise grows, right? And at some point, the noise overflows into the message. So if the noise overflows, when you decrypt, you get some garbage. And that's not interesting. So there are two ways to circumvent this. The first way is to basically, given a circuit of which you know the depth, you can pick parameters such that when you arrive at the end of the circuit, you're going to be just at the brim of overflowing, right? But your decryption will still be correct. But if you don't know the depth of the circuit, you can do bootstrapping. And bootstrapping basically takes a ciphertext that has a large amount of noise and reduces that noise. And this is like the key component that allows from going from bounded depth circuits to infinite depth circuits.
Well, what sorts of operations require bootstrapping? Do all operations require bootstrapping or specific ones?
So as I said, you can pick parameters such that no operations require bootstrapping in a bounded depth circuit, but in real life, that's not really what happens, especially in like TF-HERS, which is a library that is being developed at Zama. Like in TF-HERS, everything builds upon these small blocks of ciphertext. So for example, like a unsigned 64-bit integer is 32-bit chunks. And when you do operations on that, whether it be like addition or multiplication, then you need to add or multiply the blocks one with another, and then you need to like propagate the carryover to the further blocks, and it's quite heavy and it requires a lot of bootstrappings. Like for example, like 64-bit multiplication needs like north of 1,500 bootstrappings. So that's a lot. But of course, this doesn't fall out of the sky, right? Like, this is the result of like a heavy optimization process. And we observe that this is what runs better on CPU. Now, it's a possibility that we would find better parameters dedicated to verifiable FHE, where maybe you don't need to bootstrap as often, or there's an optimization that can be done there.
Got it. And I guess you specifically did the research on verifiable bootstrapping.
Yeah, exactly.
Using Snark, right?
Yeah.
So could you maybe just give a brief description of the research you did?
Yeah. So as I mentioned earlier, like the state of the art in verifiable FHE is pretty much doing or slapping snarks on BGV, and they avoid bootstrapping. And in that sense, our research is a bit complementary, where we don't focus about like whole circuits. We only focus on the bootstrapping, and we try to generate a proof for that.
And that's the hardest part, right?
The bootstrapping is the costliest operation in modern FHE schemes. Okay. Right. So I think it is one of the reasons why they didn't focus on that, because it's a bit complicated to do. So we had a couple of challenges trying to fit the bootstrapping inside a Snark circuit. The first one being that it's a big computation, like the size of the circuit. I don't have it on top of my head, but using Planck, we would get like a really large thing to prove. But we managed to use the fact that the bootstrapping is a heavily structured computation. So it's essentially a long for loop. So using that and also using Plunky2, which is optimized for recursion, we were able to get this sort of recursion-based IVC scheme. And that allowed us to like limit the space resources needed to generate the proof. So that's one of the challenges. Another one is also the fact that in practice, TFHE is instantiated with a power of 2 modulus. And snarks, they operate on fields, right? It's like arithmetic circuits over fields. And this doesn't really fit well together. We didn't want to emulate this power of 2 modulus inside the arithmetic circuit because it would have been like just a huge overhead. And so what we decided to do is to pick a ciphertext modulus that's prime, that fits with what Plunky2 uses. So we took this baby bear prime, and we adjusted the rest of the TFHE parameters such that we maintain 128 bits of security throughout.
And with these modifications, does that affect the security of bootstrapping at all?
No. We managed to like, so you've got a lot of parameters that you can tune, right? So we sort of like brought one down and had to bring the other ones up in order to maintain 128-bit security.
Got it. Yeah, I think that's a pretty good overview of the things you changed. Talk about maybe like kind of like the size of the proof, right? Like the challenge of that, or memory allocation, or like any memory blow up, things like that.
Yeah. Well, as I said, the memory blow up really came from the fact that like the circuit is huge.
Yeah.
And so breaking it up into like these for loop iterations allowed us to really bound the space complexity. So we didn't have this problem of a memory blow up in the end, or we were able to counter this problem effectively. And also like in practice, TFHE, as I said, is instantiated with these power of 2 moduli.
Yeah.
And with that, they use the FFT to compute polynomial multiplications very efficiently. And now that we moved to this prime modulus, we were able to use the NTT instead, which also has a linear arithmetic time complexity.
So you reconvert FFT to NTT essentially.
Yeah, with the switch of ciphertext moduli.
So this is where like a lot of hardware acceleration could also help in that process.
Yeah, for sure.
I see. And talk about some of the results that came out of this.
So the big result is that we were able to generate a proof of the bootstrapping in about 20 minutes on this huge AWS machine.
Okay. Which one specifically?
It's 21 minutes on the C6i Metal and 18 minutes on this HPC7A 96X large, I think.
Okay. This is a single bootstrap.
Yeah, a single bootstrap, 20 minutes. But it's a first step. Before that there was no timing for that. So
is this the first time ever for a TFHE bootstrap? Like someone has proven this?
Yeah.
Awesome.
Yeah, and also like we also decided to go down the route of ZK VMs, right?
Yeah.
To set a baseline of how fast we could expect this to run, and also to learn how much faster does generating a custom circuit.
So maybe just for the audience, like, can you explain what a ZK VM is?
Oh yeah, sure. Good idea.
How it works, the difference? Yeah.
Yeah. So ZK VM, maybe I should explain what a VM is. So in a few words, a VM is software that allows you to run other software, right? It emulates a computer and you can like run software on top of that software. And ZK VMs are a very interesting tool. What they allow you to do is to so they allow builders to generate proofs for small programs that they already built in some regular programming language, such as Rust, which is very, very useful if you want to like spin up a new project or whatever. And these proofs, depending on the ZK VM, they're also verifiable on chain. So this is very nice for builders, very easy to use. And the way they achieve that is that, if you wanted to generate a snark for a program that you have written in the past, you would have to sit down and like translate it from this programming language into a circuit, which is a non-trivial thing to do and a very error-prone also. And then you do all this polynomial proving on the side. But what they do, these ZK VMs, is that they've already built the circuit for the VM, the virtual machine.
Yeah.
And then what you do when you use them, you prove that the circuit for the virtual machine was correctly executed, and when you give it as input this small compiled program that you have and other input. So this is like one layer of indirection that allows for a very easy to use product, but it also gives a bit of an overhead, you know. And so, right, you get this trade-off between ease of use and overhead. And, you know, for us, we weren't able to use ZK VMs to prove a full bootstrapping. We were only able to prove one step of the bootstrapping because, as I said, the bootstrapping is a heavy operation, and these ZK VMs are more tailored for small programs.
So you ended up writing your own circuits for proving the bootstrapping in order to accomplish this, right?
Yeah, we had to. Because otherwise we could have make it work with the ZK VMs, but we would have had to dive deep into the inner workings and do like some really custom engineering, which sort of defeats the point of ZK VMs, which are supposed to be easy to use.
Got it. Yeah. I see. Okay, so with the existing ZK VMs, we were only able to do a step transition within the bootstrap.
So basically, as I said, the bootstrap is like a long for loop, and we were only able to do one iteration. Maybe we could have done a few more, but like the interesting measurement was to do one. And on that benchmark, the ZK VMs perform like 100 to 1,000 times worse than the custom circuit.
Yeah.
So yeah, really it shows that you get this very easy to use product, but with a huge overhead. On the other side, you can sit down, like spend a few months, hire a couple of cryptographers to make a custom circuit, but then you get better performance.
Yeah. Do you envision like, you know, Verifiable FHE to go towards more customized, specialized, basically ZK VMs more catered towards FHE, or do you think mainstream or like the typical ZK VMs will catch up eventually on the performance wise?
I don't think the typical ZK VMs will ever catch up compared to like custom-made circuits. Yeah. But that's kind of the same point of saying CPUs run slower than ASICs. Like, of course, they run slower than ASICs, but what they allow you to do is much more powerful. You know, they lower the barrier to entry, and everyone can program now. You know, so I think ZK VMs will be a very useful tool, and like the more time goes on, the better they're going to perform. But I don't think they're ever going to catch up to like custom-made circuits. But maybe sometime like the dark arts of generating circuits yourself will sort of disappear because ZK VMs will have become that performant.
Yeah. You know, there are FHE special FPGAs, also ZK ones. For verifiable FHE, right? Is it going to be like hybrid hardware or like how?
I think it's going to be more ZK focused hardware.
ZK, NTT, right? Just focus on NTT.
Yeah. Because like what we do, we don't. So how can I explain this? We basically put a snark over the FHE computation and not the inverse, you know? So we're not proving a snark in FHE, we're proving FHE in a snark.
Yeah.
That's the distinction. So basically the outer layer of the onion is the snark part. So that's what needs, or is going to be accelerated. Yeah.
And considering snark and starks, like, you know, have you also considered starks before?
Well, that's a funny question because that sort of depends how you define snarks and starks. So I think most people right now when they talk about snarks, they talk about air and fry. And what we used is Plunky 2, which uses Plonk for the arithmetization and Fry for the polynomial commitment scheme.
Got it.
So it's not exactly a stark. It's what I like to call a transparent snark.
Yeah. And that's because of the recursive property that you mentioned that was necessary.
So the recursive property is something that Plunky 2 made. It's not inherent to either Plonk or Fry.
Okay.
But what's inherent to Fry is the fact that we get this transparent snark. So there's no setup, no ceremony that needs to happen. It's publicly verifiable. So that's a practical constraint that we had and we wanted to achieve.
Got it. What's roughly the timeline you think for verifiable FHE to be practical?
I think it depends on the use case, of course. If I'm cheeky, I think a couple of years for this hybrid rollup to be, or maybe 1 year for this hybrid rollup to be somewhat practical. In realistic terms, I think maybe 3 to 5 years for like more general use cases.
Yeah.
To have anything that runs fast enough. And for this FHE ZKML thing that I mentioned at the beginning,
Yeah.
that's a longer timescale for sure.
Yeah. Yeah, that makes sense. Great. I guess last question is, what are you most excited about this year, happening this year in the FHE space?
Yeah, I think the traction that it's getting, the community, the conferences that are popping up around FHE, I think it's really great. I'm really happy that more and more people are getting interested in this very almost magical, cryptographic primitive. As much as snarks are magical, I think FHE is as well. And I'm really happy to onboard more people into like solving hard problems and building cool applications with that. Yeah.
Yeah, great. Yeah, I'm on the same page here. I think super excited to see what's going to happen this year. And yeah, getting a lot of interest in this space. And yeah, trying to find more builders, researchers contributing. Yeah, well, thank you so much for taking time today.
It's my pleasure. Thanks.